Okay, so this is vectors lesson 3. And let's take a look at the questions on the worksheet. All right, so what we have here, you'll notice, is more operations on vectors. So just recall that last time we saw how we could define the idea of addition and subtraction with vectors, the idea of scalar multiplication, and we have rules on how to do those things. And we already saw some characteristics that showed up. So we saw that, as with real numbers, vectors were commutative under addition. Okay, we saw that they were anti-commutative under subtraction, meaning that if I do u minus v, that's going to be the opposite of v minus u. So we're starting to see that the way in which we've defined vectors leads them to have very similar properties, to the real number system and how we work algebraically with numbers. All right, so what we want to do is see what other types of characteristics they have. So if you take a look at what, and I'm going to give you some time to think about these, but if you take a look at what I'm asking you here, is here now I'm combining 3 vectors under addition, and what I want to make sure is that the order in which I add them, so if I want to add things 2 at a time, which is how we defined addition or subtraction, doesn't matter whether I add the first 2 and then to that I add the third, or add the second and third and then add the first, and you can switch it around, the first and third. So does it make any difference? Now, I would imagine, we hope that it wouldn't. Okay, this is what's called the associative property of addition, if these 2 things are equal. Okay, here you have something that's very familiar. Is it distributive under scalar multiplication? So if I take a sum of a vector and multiply it by a scalar multiple, is that the same as taking the multiple times u plus the multiple times v? So is it distributive, the way algebraic expressions are that represent real numbers? Okay, does it make sense to consider adding a scalar and a vector? And then lastly, if we're going to define addition and subtraction, we have to consider the possibility that we're going to subtract a vector from itself. All right, so what does this mean? What would the result be? So I'm going to give you maybe 3-4 minutes to try to come up with some conjectures on these here. So because we have a very descriptive way of talking about vectors, you're not going to be proving these. We'll be able to prove these properties later on when we have a more algebraic way of looking at the concept of vectors. Okay, so 3 minutes to come up with some nice diagrams to justify these results. Okay, so we're back, and let's take a look at some diagrams here to justify these properties. So if I want to consider something like u minus u, let's consider it from our 2 perspectives of subtraction. So one perspective of subtraction is to add the opposite vector. Okay, so if I take u and I add the opposite of u, well, if I add those tip to tail, it means I have to put the tail of the second vector to the tip of the first. Okay, and then the resultant vector goes from the tail of the first to the tip of the second, which you see are in the exact same location. So that means that this resultant, whatever it is, doesn't seem to have any magnitude and doesn't really have a direction, since I'm not really moving anywhere. Okay, now if we take our other perspective of subtraction, which is to place the vectors tail to tail, and then the subtraction of the vectors goes from the tip of the second to the tip of the first, again, those things are at the same location. So there's no magnitude and no real direction. Okay, and we made reference to this earlier on, that what we need to do is we need to define what we call a zero vector. Okay, so the zero vector is a vector that has no magnitude and doesn't have any defined direction. Okay, and we need this if we want to, in a sense, complete our operations of addition and subtraction. Because if you subtract one vector from another, what do you expect to get? You expect to get 0. But of course here, since we're subtracting vectors, our result has to be a vector, which is why we have to define this 0 vector. Okay. Now, another property that the number 0 has is if I add the number 0 to any number, it doesn't change it. Well, similarly here, if I take some vector u and I add the vector 0, well, if I go to the tip of u, there's no magnitude, there's no direction, so it doesn't change the original vector. Okay, so the 0 vector really plays the same role that the 0 number plays within the real number system. All right. By the way, be sure to stop me if you have any questions. Okay. If you go to this idea of an associative property, meaning does it matter if I'm adding these 3 vectors, does it matter in what order I add them up? So let's take a look here. Let's take u plus v. Okay, so if I add those first, so there's u plus v, and then to u plus v, I add the vector w, well, there's my resultant. Okay, so this is u plus v done first and then adding w. Okay, let's try it now in a different order. If I now first add v plus w, okay, so I do this addition first, and then I do u plus that sum, well, I don't think it's too surprising that we get the exact same result as before. Okay, so this tells us that when we're adding, it doesn't matter in what order I do these additions. So this is what we call the associative property. All right. So when we go to the last one here, the distributive property, well, again, if I take u plus v, okay, and there's my sum, u plus v, and then if I say take 2 times u plus v, there you go. I get this vector here, okay? Now, let's see if the other side of our distribution works out. Let's say if first I take 2u and I add to that 2v, I see that I get the exact same result. Okay, so that tells me that vectors, okay, are distributive under scalar multiplication and addition. So these are some of the properties that we have with vectors that I don't think we should be too surprised. Okay, so here Kieran asked, what's the difference between the associative and the commutative property? Well, the commutative property just refers to 2 particular vectors. Okay, the associative property allows you to move things around, it forces you to not have to actually move anything around. Okay, so if we go back here, if I take u plus v, these here, I don't have to first use the commutative property. It just means I can do whatever addition first. Okay, so slightly different, but definitely offering similar results. All right, so let's take a look at these. Let's take a look at the notes here for a second. All right, so here we have this definition of this 0 vector. It's something we're defining. Why are we defining it? Because it's useful, okay? And it doesn't contradict anything else we had before. All right, and these are some basic properties of vectors. Now, again, we haven't proved any of these. We've just demonstrated that they're reasonable. Eventually, we will be able to prove any of these. So we saw here commutative property we did last time. Okay, we saw the anti-commutativity of subtraction last time. Now we showed that it makes sense to define this 0 vector. It allows us to define a subtraction of a vector by itself. Adding 0 to any vector doesn't change it. Here's our associative and distributive properties. And there's a couple of others here which we're not going to go through. I think they're pretty reasonable, so we're not going to necessarily justify them here, but again, you'll be able to prove them later on. This is a particularly important one. Can somebody tell me what this allows us to do with vectors, similar to what we're allowed to do when it comes to variables?
So, like, yeah, factor.
Okay, factoring. Yes,
And
there is a factoring involved, but I want you to think of going in this direction here. What does this look like, where I have some number times perhaps an unknown plus another number times that same unknown?
we can group group variables.
There you go. It looks like we're grouping like terms. That if this is 2v plus 3v, well, that's the same as 2 plus 3 is the same as 5v. Okay? So at a certain point, what you start to see is that these properties tell us that we can deal with vectors in a very similar way that we deal with algebraic expressions that are involving numbers. Okay? Meaning we can distribute, meaning we can group together, meaning the order in which you add doesn't matter. Okay? So all those things that we were able to do with algebraic expressions, we are now able to do with vector expressions. Okay? So just to get a little bit of practice on that, let's go back to the worksheet here and let's look at these two examples. Okay? So if I were to replace u, v, and w by x, y, and z, it would look a lot like an algebraic expression. And what would you use? You would use distribution, you would use commutativity, you would use associativity. You would bring together like terms to simplify the expression. Well, because of these characteristics that we just justified, we should be able to do the exact same thing because all those properties apply to vectors. Okay? Then I want you to think about what old trick that you would have used with algebraic expressions to help you answer this question here. So I'll give you maybe 4 minutes, 4 or 5 minutes to work on this. Before we get to that, does anybody have any questions as to what we've covered up until now? Okay, so I'll give you. Oh, yes.
Tony, I just wanted. Yeah, sorry. I'm just still a little confused about how associative really differs from the commutative property, because in either case, then it's just the fact that you can sort of rearrange the variables, which will end up in the same result.
Okay, so let's go back to associativity here. Okay, so let's say you have u plus v plus w. Okay, well, when you have u plus v plus w, really the only thing you could switch around would be the u and v and make it v plus w. Okay, the only thing commutativity tells you is that you can separate any two variables. That you can switch the position of any two vectors in an addition. Okay, it doesn't tell you anything about adding multiple vectors together. Okay, this gives you the ability to add multiple vectors together. The only thing commutativity talks about is an operation between two vectors. This justifies that multiple vectors can be done in any order. Okay, it's a subtle difference. I can see the confusion there. It is a bit of a subtle difference, but the only thing commutativity tells you is it works with two vectors at a time. This allows you to do the operations in any order you like, okay, without having to flip them around every time. Okay, so I don't know if that clears it up.
Yeah, that's good. Thank you.
Okay, so let's take some time to take 4 minutes to work on these. Okay, this one's pretty straightforward. This one here, think about what tools you might use that you've seen in the past to write x and y in terms of only u and v. Okay, so we'll be back in 4 minutes. Okay, folks, so we're back. So let's take a look here at I'd answer this problem. Now, before I, let's look at the first one here. So you notice here that I just treated this expression in the same way I would treat an algebraic expression, because all those same properties that I use for algebraic expressions, I can use for these vector expressions. So I apply the distributive property. By the way, this is probably more steps than I would expect you to show, say, on an evaluation. I'm just trying to be very explicit as to what's going on. So here we're applying the distributive property. Okay, here we're moving things in any order we like. So we're grouping together all the essentially like terms. We might as well use that same language. And then here I use that property that allows us to combine these like terms to get 15 times vector u minus 7 times vector v plus, well, we see that these things add up to the 0 vector. But because another one of our properties is that the 0 vector has no effect on the other vectors that are there, I don't have to write it. So yeah, so Kieran, like I said, I'm just kind of showing things a little more explicitly, but of course I would not expect you to write plus 0 vector and then to eliminate it, okay? In fact, I would say you probably go from, here to there, and then there straight to the answer, okay? Would I force myself to write this first step? Yes, because as we know, the most common types of errors are those sign errors, and you want to avoid those as much as possible, all right? So can somebody tell me what this question might have been similar to? What did it kind of look like? Did anybody come up with a way? Yeah, it looks a lot like solving a system of equations. All right, so that's what I did here. Now, there's different ways in which you can do this, but all those properties, again, all those algebraic properties of addition, subtraction, commutativity, associativity, all allow us to treat this like a system of equations. So if I call this equation 1 and equation 2, all I did was I first eliminated the vector x by doing a particular multiplication. And again, when two things are equal, whatever I do to one side, I have to do to the other side to keep them equal. And then from there, I can add the left sides to end up with an expression for vector y. Worked out pretty nicely because I didn't have to do any division or scalar multiplication of the reciprocal. And then similarly here, I just multiplied both of these equalities, and from there I was able to solve for one of them. So somebody's asked, could you isolate and substitute? Of course. Again, that's the substitution works under the same principles as elimination does. Okay, so you certainly could use that, because in the end you would just be substituting something that was equal and then still applying distribution and addition, subtraction, all those same properties. Okay, so again, this tells us that we have quite a few tools when we're working with multiple vectors that are being added, subtracted, and having scalar multiples applied to them. All right. So what we want to look at now is a couple of examples that are maybe not completely related, but just some good review questions. Okay, so here this would be similar to something you probably would have solved in the homework, and here you just have a couple of examples of adding and subtracting vectors. Now, one thing here, you'll notice that, again, I'm trying to trying to show you the different types of notation that we can use. So this is something that a lot of you are probably familiar with, using the square brackets around the direction. Okay, so whether you use them or don't use them, I'm not going to be picky about that, but that is certainly a valid notation. Okay, and keep in mind here with these two examples, How in this case here, the vectors are given explicitly with an explicit magnitude, explicit direction, whereas here, the magnitudes are given explicitly, but the angle is given with respect to each other. So this is where, you know, a good diagram is going to be helpful for solving these here. So this might take a bit of time. So what I'll do is I'll give you about 10 minutes to work on these. Okay, folks, so we're back. So I may have mentioned this already. So obviously, some of you, depending on how the vectors are given, use the idea of breaking up a vector into a horizontal and vertical component and working with those. And it's perfectly fine if you solve problems that way. I'm just going to stick to one method because we're actually not going to spend a lot of time working with these, what we call geometric vectors, which are vectors that are defined the way we're defining them, as some magnitude given explicitly with some direction, either with respect to each other or with respect to a cardinal plane. That's actually going to be something that's going to be short-lived for us. So I'd rather just sort of keep things simple. All right, so this question number 4, besides having done it in your homework, you actually probably would have solved this question in grade 9 without me necessarily using this notation, of course, but you would have determined the length of a diagonal in a cube or rectangular prism. Okay, certainly those of you who took grade 9 with me, you definitely would have solved this problem. And what's the key ingredient that you're going to use to solve this problem? What's that key characteristic in a cube that's going to make this easily solvable?
The fact that all sides are equal.
Actually, in this case here, it's not even that important that they're all equal. You could solve a very similar problem with a rectangular prism.
That all angles are 90 degrees.
There you go. It has to do with the fact that all sides are 90 degrees, meaning that you can just keep reusing Pythagoras to solve these problems. All right. Now, of course, I suppose you could solve something which would be slanted, but you'd have to be given some angles in order to use the sine and cosine law. So here, if I want to determine AG, well, it's about first determining this length AC. Okay, and that's part of a right angle triangle. Okay, so you can use Pythagoras, and then working with AC and CG, of course, using, in this case here, AC would just be A plus B, okay, and then A plus B, and add vector C, which is the same one there, and guess what that produces? Another right angle triangle. So when you think about it, this definitely would have been solvable back in grade 9. Okay, so if we take a look at the solutions here, okay, let me move this over just a little bit. So first, how do you get to AG? Well, we just said it. The vector A plus the vector B plus the vector C gives us AG. CE, that one there, well, here, so I kind of started with C, I go up, and then I went that way, which would have been subtracting vector A, okay? And then in that direction there, you see the opposite. I'm adding the opposite of B, so subtracting vector B. And then BH, I guess, would be pretty similar, whereas BH, I guess, would be that vector there. So how did I do it? I did B plus C, and then plus the opposite of A, so minus vector A. All right? So again, that comes through from the that comes through because vectors are movable wherever you need to move them. Okay, so here there was a could you also just say that all side lengths are the same, therefore A plus B plus C are equal? Are you talking about part B? Yeah, I mean, in principle, I would like to see how you actually get to that length, okay? So in the end, that's what you're doing. But I think I would expect you to tell me how you actually measure that length, and then confirm that is indeed equal, okay? Yeah, I feel like it needs a little more justification. In the end, I just went through the process that I talked about. Okay, how do I find this length here? Well, I can just use Pythagoras because it's a right angle triangle. And then when I'm working with this triangle here, again, a right angle triangle. So it's the magnitude of AB, okay, squared, plus the magnitude of C squared. But we already determined that the magnitude of A plus B squared was equal to the magnitude of A squared plus the magnitude of B squared. So you end up with this expression, which of course, now that I look at it, you could simplify this because they're all equal. So you could just write it as the cube root of 3 magnitude of A squared. Okay, that would have made it even simpler. And then you can get to the exact same result going in the direction I did here. First finding this side length and then creating that right angle triangle with the diagonal, that side length, negative A, and then B plus C. Okay? So now what I want you to keep this question in mind, because this is going to come back to be useful for us a little later on. And I hope that you can see that using this methodology, okay, doesn't require any of these side lengths to be the same. The way I did the problem would work equally well if the length, the width, and the height were all different numbers, okay? So that's what I want you to keep in the back of your brains there, because at some point, this is going to come to be very useful for us, and we won't necessarily be working with a cube, but with a rectangular prism. Okay, any other questions on this one here? Okay, so real quickly, the other two. Now, I believe in the last example that was similar to this one here, I think I placed these vectors tail to tail, okay, which is a perfectly reasonable way to solve the problem. This here, instead, I decided to add the opposite of the second vector. So I placed them tip to tail, but of course, I have to find the opposite of that second vector. So it's just a matter of switching up south and east to north and west. And so from there, I did something very similar to what I'd done before. I start with my first vector, little cardinal plane, draw it. At the tip of that one, draw another cardinal plane, so I can now draw the tail of the second vector, okay? I just use some angle properties here. This is 25, so that's also 25. So this is 25 plus, well, this is just going to be 90 minus 15, 75. So that's where I got the 100 degrees, okay? So I start off by using cosine law to determine the magnitude of the vector. Now, what's nice about this version of subtraction is that I already have my vector resultant at a cardinal plane. So if I just determine what theta is, I can just add that to 25 to describe the direction. And again, you'll notice that I choose to use cosine law, because anytime I'm working with one angle and two side lengths, I worry about running into the issue with the ambiguous case of sine law. So that's why if I use cosine law, I know I don't have to worry about that. All right. And the second one here, this is again another one of those things we want to keep in mind, that when we are given these two vectors, the angle between them is when they're placed tail to tail, okay? But if I want to add them, it's going to be easier to take this vector and move it over so that they're tip to tail, okay? But that means that the angle 110 is not in the triangle that I'm working with. But because this vector is equal to that vector, they're parallel, I'm able to use my parallel line principle, that this obtuse angle and this acute angle add up to 180. So now I've got all the information I need because I've got 7 and 5, the angle between them. So again, you can use cosine law to find the magnitude. And then I find this angle theta. Again, just to make sure I don't have any issues, using the cosine law, I find this angle. And the way in which I describe the direction is with respect to the two vectors. I say it's 68.34 from U towards V. Okay? Now, obviously, if you had solved the problem by, drawing the 7 here and the 5 there, then your direction would be given slightly differently, but it would be equivalent. All right? So, the main thing to get out of this lesson are our properties of vectors, okay, that we were able to justify with some, some fairly easy diagrams, which means that we can essentially work with expressions containing vectors in the same way that we work with expressions containing algebraic expressions. All right? And then here, just a couple of review questions. So any last things we want to ask before we end this off?